In this video, we'll discuss the addition of carbenes to alkenes. So if we can remember back to when we talked about reactive intermediates, a carbene is a neutral carbon compound that has two atoms bonded to it and then a lone pair of electrons. Since it doesn't have a full octet, it's pretty reactive still, and so these guys can react with alkenes to make cyclopropanes. So this pair of electrons is going to go to one of the carbons, and then the pi bond will come out and hit this guy, and then you end up with a cyclopropane with whatever those R groups are on it. And there's two main ways that we do this. Carbenes are very reactive, so you want to generate them in situ or in solution. Otherwise, they're going to react before they get a chance to see your alkene at all. And some of the precursors for carbenes are fairly explosive, so these next two methods are about the safest ways that you can generate a carbene and then have it react with your desired reagent. The first way is called the Simmons-Smith reaction, named after the two guys at DuPont that came up with it. And so in this case, you take diiodomethane and you add to it zinc with a little bit of copper impurity, and you make an organometallic intermediate that behaves kind of like a Grignard. So we call this guy a carbenoid. It's not quite a carbene because it doesn't have the full lone pair, but the zinc is sort of inserted itself between the iodine and the carbon, like what we see with the Grignard, and that makes it fairly reactive. And this can react with an alkene to give us cyclopropane. So if we draw the structure out, I've got two H's, an iodine, and then this zinc iodine type structure, and then I can have some alkene. So essentially what's going to happen is, if we think about this zinc iodide, it's going to behave a little bit like the Grignard would, and so this pair of electrons here can come onto there, these can go here, and my iodine leaves as in the leaving group, and I end up with, and I'm going to draw it down here, my carbon here, still with the two H's on it, and then you have in solution basically zinc I2. So the zinc can coordinate to both of those I's, the one that left and the one that was already on it. The other way to generate a carbene is from what we call alpha elimination, and this happens by starting with a carbon that has one H on it and then several halogens. So the halogens are very electronegative, which means that this hydrogen is actually fairly acidic because of all that electron density being pulled away from it by those halogens. So we could use a tribromo or a trichloro compound. What we do then is put that in solution with a hydroxide base, and that can deprotonate this guy. And then we end up with a carbanion plus water, and this bromine can leave to give a carbene, which is still quite reactive but is no longer charged, and then Br minus, which is a good leaving group because it's a large atom and fairly electronegative, so it can handle that charge. And then we've generated this carbene in solution, and that carbene can then react with a double bond in order to make a cyclopropane. In this case, it would be a dibromocyclopropane. So let's go to the next slide and we'll do an example of that. So if we look at an example here, and I'm going to use some stereochemistry to demonstrate a point, and that is that this is a stereo selective reaction. So in this case, I'm starting out with this alkene, and it is trans, and that my two largest groups are opposite from one another. What I would put in solution then is my CHBr3 under basic aqueous conditions, and what I would end up with down here would be my carbon with the two bromines on it, and I would have still that trans stereochemistry. So here I'm trans, and there I'm trans. So if your alkene has a certain stereochemistry associated with it, cis or trans, it will remain that way after the reaction is over. And that's because this is a concerted one-step addition of the carbene to the alkene, so the stereochemistry remains the same. So we'll go to the next slide and look at that, what's happening there. So we had our 2 phenols and our 2 H's and our trans. There's going to be that intermediate after the deprotonation and the leaving of the bromine. I get my carbene intermediate, and so in one step this comes down and makes that cyclopropane ring, and so because it's coming and sitting down on top of it, those phenols stay opposite one another. If they had been on the same side cis, then it would have gone on the same side. So now I get that 3-membered ring with my 2 bromines coming off, and my phenols will just be on opposite sides of one another on that ring. So one will be coming out the front of the ring and one will be going out the back of the ring.